Okay. So there are three types of addresses that we have in both IPv4 and IPv6. In IPv4, we have like unicast addresses. In IPv4, we have multicast addresses, and in IPv4, we have broadcast addresses. When it comes to IPv6, we still have unicast and multicast, but in IPv6, we don't have broadcast. We have anycast instead, which is like one to nearest communication. So unicast again, unicast addresses in both IPv4 and IPv6, they are used for one-to-one communication. The challenge with the unicast address is that if there is only one sender and there is only one receiver, then in that situation, the unicast address is going to work fine. There is not like any problem in that. If there is one sender, one receiver, like this device will become the sender, this device will become the receiver, or vice versa. So if there is only one sender, one receiver, then it's fine. Then it's okay. Then in that situation, like unicast addresses can be used for like one-to-one communication. But sometimes what happens, like we need to send the data, not to one, but multiple receivers. Like we might need to send the data to, like, let's say, for example, 3 machines, 3 receivers. So we have like a few ways that we can use to achieve the same task. Like we want to send the traffic, we want to send this packet to multiple destinations, like multiple, like this is the receiver, this is the receiver, and this is also the receiver. Same copy of the traffic has to be delivered. Same copy of the packet, same copy of the traffic, same traffic, in fact, has to be delivered on these 3 machines. There are like total 3 ways again of doing the same. So if you have, like, let's say, for example, a sender, one sender, and you have multiple receivers. So what you can do, first of all, like you can use unicast method to forward the traffic. In case of unicast, what will happen? You will generate the packet and you will send it to, first of all, this destination. Then you will generate the packet and send it to this destination, and then generate the packet and send it to this destination. Like you need to generate like 3 messages. Every message will have its own set of source IP and destination IP. One packet will be delivered here, one packet will be delivered here, one packet will be delivered here. So it will be again like one-to-one communication. So there is one sender, multiple receiver. That sender generates like 3 copy of the data, and it sends 1 copy to the first receiver, second copy to the second receiver, third copy to the third receiver. So we can use like unicast for the same. Unicast basically means the sender needs to generate multiple copy of the frame, and it needs to send that multiple copy to all these like receivers one by one. The problem with the unicast is that here, in this approach, in this case, problem with the unicast is that same copy is being generated by the sender again, like 3 times at least. 3 times the data is moving from this link. So it is utilizing the resources, link bandwidth, CPU utilization, and all that thing is also there. So you doing the unicast in like n number of receivers like might not be a very good idea. So we can use the thing called broadcast, where the sender will generate 1 packet only, and the packet will have the source IP of its own IP, but the destination IP is going to be the broadcast IP. Broadcast IP is going to be like 255.255.255.255. Packet will arrive on the switch. Switch is going to forward that packet here, here, and here, because broadcast basically means like one-to-all communication. So packet will be received here, packet will be received here, packet will be received here. So sender does not need to generate like 3 packets unnecessarily. Packets are not going to necessarily utilize the link bandwidth. Only 1 packet was sent, and that packet was delivered to all the destinations, all the receivers. So broadcasting could have been like one way to send a copy of the traffic to multiple devices. However, the problem of this broadcasting is that there might be some machines who are not interested in receiving that particular traffic. But since we are doing the broadcast, these devices will receive the traffic. They will have to process that traffic, and then later on they will decide that, okay, they want to drop it. Remember, in a broadcast packet, let's say this is a data, and this data is being broadcasted. Remember, when the data is being broadcasted, the destination MAC is going to be all F, and the destination IP is going to be 255.255.255.255. So when the packet is received on the receiver side, no matter if it wants to receive it or not, it does not matter. When the data is received on the receiver side, first of all, the device is going to check the data link layer header. In the data link layer header, it will find that the destination MAC address is broadcast MAC address, which means like I need to receive this data. So it will receive that data, it will decapsulate that header, then it will check the IP header, check the destination IP. Destination IP is 255.255.255.255. This machine will see that, okay, this packet is being broadcasted, and since I am the part of that broadcast domain, I must receive that packet. So it will decapsulate that, it will remove that IP header, then check the maybe, for example, like UDP header, TCP header, whatever, and based on that, then it will decide if it needs to accept or drop the data. Maybe, for example, the traffic is for the destination port number 23, destination port number 22, destination port number like maybe 2021, whatever. So based on that, now it will decide if it, let's say, for example, the packet is for the destination port number 80, and you are not running the services of destination port number 80, that means you will drop that packet. So packet is getting dropped all the way to the transport layer, all the application layer. Packet is not getting dropped on the data link layer or the network layer. Basically, the device, if in simple terms, if a packet has been broadcasted, the packet will be received by the device in the broadcast domain. Packet will be processed by the device in the broadcast domain, and later it will be decided if the packet needs to be dropped or needs to be processed, actually. Which again, like if there is one sender, and there are multiple receivers, it's fine. But only these two devices were willing to receive that traffic. These two devices, they are not willing to receive the traffic. These two devices, they don't belong to that if I say broadcast domain, these two devices, they are not, they are part of the same network, but they don't want to receive the traffic that is being broadcasted by this sender. So the point is that we want to send the traffic to multiple devices, but actually we want to send the traffic to multiple yet specific devices. It's not like we want to send the traffic to all the devices. No, we want to send the traffic to multiple yet specific devices. These two devices must not receive the copy of the data, and these devices must receive the copy of the data. So broadcasting is also not going to work in that situation. Broadcasting will not work in that situation as well, because if you do the broadcasting, the packet will be broadcasted, will be received by all the devices in the broadcast domain, no matter if they want to receive the traffic or if they don't want to receive the traffic. Later on, when they recapsulate the traffic, then they will decide if the packet has to be accepted or the packet has to be actually dropped. And of course, like when it comes to any cast in IPv6, any cast is one to nearest communication. It like the traffic will go to the specific destination in this case as well. So this cannot be used to send the traffic from one device to multiple devices. So we have a sender, we have multiple yet specific receivers, and we want to send the traffic to those specific receivers. We don't want to send the traffic to all of them. So a unicast, doing the unicast is possible, but not very much feasible. Doing the broadcast is possible, but not very feasible. Anycast is not even going to work in that situation, because anycast is a different type of addressing. So the only technique that is left in that situation is referred to as the multicast. So multicast is a technique. Multicast in both IPv4 and IPv6 is a technique to send the traffic to multiple yet specific destinations. There is a sender, there are multiple receivers, but these are specific receivers. This is receiver number 1, this is receiver number 2, this is receiver number 3. This is like one sender, and this is like receiver number 1, receiver number 2, receiver number 3. There are 3 receivers. There is one sender, there are 3 receivers. There is one sender and there are 3 receivers in here. This device is also part of the same network, same broadcast domain, but this device is not the receiver. So in these kind of situation, multicasting the traffic to the destination is going to be much more suitable, because when we do the multicasting, the traffic will be received on multiple yet specific destinations. Remember that switches, they don't have the capability to differentiate between the multicast and broadcast traffic by default. Like if this is a switch, this device sends a broadcast packet, that will be flooded. And if the device sends a multicast packet, that also will be flooded. The switch is not going to actually switch don't have the capability, switches, these devices, they don't have the capability to differentiate between a multicast and the broadcast address. Not at least by default. By default, these switches cannot differentiate between the multicast and broadcast traffic. That means if a switch receives a broadcast traffic or a multicast traffic, packet will be broadcasted to all the devices. All these devices that we have. It will be on the devices then if they accept that traffic or they drop that traffic. So in a way, like here, like for example, here, bandwidth is still being wasted. But at least like the device is not sending multiple copies of the frame again and again. The device doesn't need to generate multiple copies of the same frame. It doesn't need to unicast it on those destinations. So it has like multicasting has obvious benefits. So what is multicast? Unicast addresses are used for one-to-one communication. So that one packet might be required if more than one packet might be required if the data has to be delivered to the multiple destination. So here is one sender, here are 3 receivers, and we want to send some traffic to all of these recipients. I want to send the traffic to all of these receivers, and we are going to use unicasting for the same. That means the server need to generate 3 messages. Those 3 messages will get routed in the entire network, and then they will be delivered onto the respective machines. So more than one packets might be required if the data has to be delivered onto the multiple destination. Broadcast is going to eliminate this. In case of broadcasting, the packet will be like one packet will be generated and everyone is going to receive the copy of the same. But the problem in the broadcast is that this device was the intended recipient. That means here I wanted to send the traffic, but here I did not want to send the traffic, but still the packet will be delivered because broadcast means one-to-all communication. So every device in the broadcast domain will receive the copy of that thing, no matter like if you want it or if you don't want it, it doesn't matter. So broadcasting will eliminate this requirement of generating multiple packets and sending to all these destinations one by one. In broadcasting, only one packet will be generated and that will be broadcasted to all the devices. But the problem is that the packet might also be received by the devices which those were not supposed to receive the packet. However, in case of multicasting, server generates the packet, multicasts that packet. That multicast packet is going to be received to only those devices who have subscribed for that particular traffic. A multicast packet is only delivered, a multicast packet is only received successfully by only those devices which have subscribed for that particular, if I say traffic or if I say stream, it's going to be the correct word. So it's like the server is going to multicast the traffic. And when the traffic is received by these intermediate devices, they are going to multicast it towards the destination as well. And since these two devices have not subscribed for that particular traffic, they will not receive it. But this device has subscribed for the traffic. Only this device will be able to receive the copy of that particular data. These devices will drop that traffic at the data link layer level. They will not even process it furthermore. They will receive the packet, check the destination MAC address. Destination MAC address will not match with their own MAC address, and they will just drop it. A very good example of this is, let me explain you from the routing protocol point of view. So this is a router, this is a switch, and here we are running multiple routers. Here we have a LAN, A, B, C, D, and E. I want all these LAN devices to reach to each other. So that what we have done. So to make the reachability, we have decided to use a routing protocol for the same. I will go on all these router and I'm going to configure a routing protocol. And I have decided to use the routing protocol named as RIP version 1, RIP version 1. In the RIP version 1, what happens? Like when this router generates the RIP update message, this RIP update message is going to be broadcasted. That means that RIP message will have the destination IP as 255.255.255.255 at the network layer and the destination MAC address as FFFFFF at the data link layer. Packet will arrive on the switch. Switch will check the destination MAC address. Based on the destination MAC address, switch will forward that packet to router 2, router 3, router 4, and router 5. All these devices will receive that RIP packet. Once they receive that RIP packet, they will decapsulate the data link layer header. They will check in the data link layer header, the destination MAC address is actually FFFFF, which means the frame is being broadcasted. And since I am part of that broadcast domain, I must receive that frame. Then they will forward the packet to the network layer for further processing. At the network layer, destination IP is 255.255.255.255, which is also a broadcast IP. That means these devices will have to receive that particular packet, and they will further process it to the upper layer, which is the UDP. RIP uses UDP. Now at this point, this router checks if the UDP port number 520 services are running or not, because this is for RIP. So if the UDP port number 520 services are running, then I will accept that packet. If the UDP port number 520 services are not running, another way of saying RIP routing protocol we have not configured here. So this device will drop the packet at the transport layer. It will not drop the packet at the data link or the network layer. Packet was received by the routers, packet was processed by the router, and later on when the packet was handed over to the transport layer, then it was decided that we are not running that services of RIP, so I need to drop it. I need to accept it. I need to drop it. So the decision is being made at the transport layer from the routing protocol point of view. In contrast to this, if we were running a protocol such as EIGRP, or if you're running a protocol such as OSPF, or if you're running a protocol such as RIP version 2, if we run a protocol such as EIGRP update messages are not broadcasted, they are multicasted on the multicast address 224.0.0.10. So the destination IP is it is not a broadcast IP, it is a multicast IP. And then a destination MAC address is also going to be a multicast MAC address derived with the help of this multicast IP. So now this EIGRP message was generated by router number 1. This EIGRP message got encapsulated by IP and data link layer header, and the packet was given to this intermediate switch. Intermediate switch receives that packet, checks the destination MAC address. This switch cannot differentiate between the broadcast and multicast MAC address, so it will treat it exactly the same. It will broadcast it. It will flood it out of all the interfaces except for the interface where the frame was received. It will flood it. All the routers, router 2, router 3, router 4, router 5, all the routers will receive that EIGRP packet, but only and only those routers will be able to successfully process that packet where we have run EIGRP. Because when we configure EIGRP routing protocol on any of the router automatically becomes part of a multicast group 224.0.0.10. This router automatically enables this capability that I will receive the traffic for I will receive any traffic for the destination 224.0.0.10 automatically. When we configure EIGRP on the router enables this capability that I will send the packet to the destination IP address of .10, and I'm supposed to receive all the messages that are sent to the multicast address 224.0.0.10. So we have enabled EIGRP here. We have enabled EIGRP here, which means these two devices will successfully be able to receive the packet. But since we have not enabled EIGRP on this router, and we have not enabled EIGRP on this router, they are not part of that multicast group 224.0.0.9. That means when they receive the packet, right at the data link layer, they will drop that packet. The packet will not even be processed at the network layer. They will check the destination MAC address, not matching. Destination MAC address is a multicast MAC address, and I am not part of that multicast group because I am not running EIGRP. So I'm not going to accept that particular message. Same goes for OSPF, same goes for RIP version 2. RIP version 2 uses .9, OSPF uses .5 and .6. We have already explained it. Why it happens like when we multicast any traffic to 224.0.0.6, why it happens that only DR receives it? Because when we configure OSPF and a router becomes DR, it considers itself part of the multicast group 224.0.0.6. So any packet that is sent to that multicast address, it can receive. Only that router who has become DR can receive that packet. This is the very basic operation of the multicast. In multicast, packet is generated and sent by the device, and the packet has the destination IP and MAC address as multicast MAC address and multicast IP address. And based on that, the devices decide if they have to receive that multicast traffic or if they don't have to receive that multicast traffic. If they are part of, if they have subscribed for that traffic, if they are configured to receive that traffic, then they will receive it. If they are not configured to receive that traffic, they will not receive it. If they are part of that multicast group, they will receive it. If they are not part of that multicast group, they will not receive it. This is the simplest operation of the multicasting that you can see. Doubts, let me know. Any question, anyone? All these topics might be completely new to you. So focus on these topics very much. You might not have covered multicasting anywhere previously. So any doubts, if you have, let me know. Okay. Yes, Devashish.
In case of EIGRP or OSPF, when you say the switch will not cannot identify
Yes, yes.
multicast MAC address and broadcast MAC address, means why is that?
Because like multicast and broadcast, how the switch is going to see, since the multicast MAC address are derived automatically with the help of the multicast IP. So the multicast IPs can be used, like any multicast IP can be used for the multicast traffic, and you cannot hard code the switch to understand like all the multicast IPs. So it cannot,
Okay,
not even
if
for the well-known protocols.
mhm. So if anything anything running, any interface is connected to any router that is not running EIGRP or any protocol that is not intended for the multicast traffic, will that EIGRP means update will also go to the
Definitely. Yes,
interface?
yes, yes, yes. Switch will forward that multicast packet towards that particular router. That is correct. Right. The switch will receive that multicasted message. It will multicast it, basically flood it to everywhere. It is ultimately on these devices then to drop that packet or accept those packets.
Okay.
We can also enable a few features if you want. Like if you want to give the switch capability to understand the multicast range, we can enable some feature for the same. But like for that range 224 traffic, the packet is always multicasted. So like we cannot have like any special treatment for those messages. But for general multicast, we can enable some capabilities so that the switch understands what exactly is multicast message and what exactly is a broadcast message. But by default, no.
Okay.
Yeah. So multicast has a lot of advantages, such as, for example, enhanced efficiency. Like it controls the network traffic and reduces the server and CPU overhead. A packet might not be generated by the server again and again. One copy of the packet is generated and it is multicasted throughout the network. So it controls the network traffic and reduces the server and CPU overhead. Optimized performance eliminates the traffic redundancy. Again, same packet does not need to be generated again and again. Now it is possible that we can run certain services on multiple servers. Like it makes multi-point applications possible. Like this is a server, this is a server. Both the servers are responsible of sending the multicast traffic. So multiple points can be there, multiple senders can be there, and the receivers will be able to receive that traffic, not in a redundant way. It's not like this will also receive, this will also receive. The receiver will receive one copy of the traffic only, which is possible with the help of the multicasting as well. Multicasting supports distributed application. That means not only one, multiple servers, multiple senders can be there for the multicast traffic, and the receivers are going to receive the traffic accordingly. It's not like receiver will receive like multiple traffic, they will receive only one traffic for the same. So the multicasting enhances the efficiency, optimizes the performance, it makes the distributed application deployment possible. However, there are certain disadvantages as well. For example, multicast is the best effort service. That means like there is no TCP, UDP used in multicast is pure IP or MAC. So there's no like TCP involved, nothing like that. So multicast is the best effort service. That means the packet might get dropped during the transit. So multicast applications, it becomes the responsibility of the multicast application to deliver the packet to deliver the data from one point to other point accordingly. Like there is no such thing as reliable multicast. Like maybe in near future you might see reliable multicast, but at the moment the multicast packet that are delivered are completely unreliable. It is the responsibility of the multicast applications, the application program from where you are joining the stream or you are sending the multicast traffic. It is the responsibility of those applications. A developer must design the applications in such a way that if some traffic gets dropped, then some sort of retransmission and those things can happen. It is not the responsibility of the multicast itself to do anything about the same. There is no congestion avoidance. So if like multiple messages are being sent, congestions might occur. There is no TCP windowing, slow start mechanism. So because of multicast, congestion might occur in the network. So again, it becomes the responsibility of the multicast application to attempt to detect and avoid the congestion conditions as much as possible. So whatever multicast application you are using in your production environment, that application must be designed in such a way that it can handle the drops, and it must be designed in such a way that it deals with the drops. Like if the packet gets dropped, how the multicast application is going to deal with that has to be there, and it must have some sort of condition avoidance mechanism built in as well, because that is not the responsibility of the multicasting. Duplicate packets might be received in the multicasting. So your multicast application must be designed to expect some duplicates messages in the multicast delivery. So multicast application should be designed to expect occasional duplicate messages. Out of order packets means like I send 10 packets, the packets might not get delivered in the same order. So multicast applications might also must also be designed considering the fact that the packets might not arrive in order, like they might arrive out of order. So best effort delivery, no condition avoidance mechanism, duplicate, out of order delivery. These are some disadvantages, if I say, of the multicasting, and these are some advantages that we have for the multicast. The biggest advantage of the multicasting remains the same, that we don't need to send multiple data frames. One data frame will be sufficient to be delivered on multiple yet specific destinations. Now, to support multicast, we need three things and three things only. To support the multicast, we require three things in total. So we are going to cover those three things, and that will finish the multicasting as per our content. So there are three things that are required to support the multicasting. First, how are we going to identify the multicast group? I am saying that these three are the devices that are supposed to receive the traffic. That means if I send the traffic, it must be delivered on these three devices. So a group of these three devices. How are we going to identify this group? There must be a set of addresses by which multicast groups are identified. To support the multicasting, three requirements are there. First requirement is that there must be a set of addresses by which multicast groups are identified. There must be a set of addresses by which multicast groups are identified. Okay. Second, there must be a mechanism by which the users, the end users, they join the group and they leave the group. There must be a mechanism by which a host can join and leave the group. When the host wants to receive the multicast traffic, it will join the group where the multicast traffic is being sent. And if the user does not want to receive the traffic, then it should leave the group so that it does not receive the multicast traffic unnecessarily. Okay. So first, let's talk about these two. So consider this diagram here. I have here a router. This is going to act as the sender, and here we have like three, maybe four receivers. and they are connected via some sort of switch. Remember that in GNS, the switch that we have, it is just a basic switch. It does not support anything. So I'm just going to zoom it. Okay, so these are, I'm going to change the symbol of it to computer. This is going to be group member number 1. I'm going to change the symbol to computer. This is going to be group member. This is going to be group member number 2. This is also, I'm going to change the symbol of it to computer, and this is also the same. This is going to be group member number 2. This is going to be group member number 3, or maybe not the group member, non group member. It's not a group member, and this is also not a group member. For the moment, this is also not the group member, and this is the group member. So here we have a server. This is a server. Change symbol. This is server, and I'm going to call it M source. M source means source of the multi. MSOURCE. So this is the source of the multicast stream. This is the source of the traffic, and these are like the group member. Group this one, and these are not the group member. And okay, one more thing. It's not like we can run multicasting without unicasting. So you need to configure the IP addresses and everything anyway. To support multicast, the unicast addresses have to be configured. Multicast routing cannot run alone. If you want to configure the multicasting, you have to configure the unicast routing as well. So currently, what we need to do, we need to configure first of all some IP addresses on here. So 192.168.10.100. Okay. So let me just quickly configure the IP address on all these devices. So let me quickly configure here. So first interface, this is Ethernet 0x0 everywhere. FA 0x0, as you can see, 0x0 here, here, and 0x0, 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 everywhere it is 0x0. So I'm going to actually here interface FA 0x0 and going to do the no check. And the IP address 192.168.10. On server, I'm going to configure it as 100, and on rest of the devices, I'm going to configure it something else. For example, here I'm going to configure it as 5. Here I'm going to configure it as 4. Sorry, 3. Here I'm going to configure at 2. And here I'm going to configure it as 1. So 192.168.10.1, 10.2, 10.3. This is 10.4 actually. 10.5, whatever you consider, doesn't matter. And here is the multicast source. Right. So let me just quickly do the ping. And I'm going to actually capture a few, like capture this one. I'm going to capture this one as well. And then I'm going to capture this one as well. That is enough. You can do the capture on the rest of the links as well. Not needed actually. So I will go on the show IP int brief first of all. Let me check the IP address. So on the interface FA 0x0, here IP address is configured. Here IP address is configured. Here also the IP is configured. Here also the IP is configured. Here also, everywhere basically we have configured the IP address. Now what I'm going to do, I want to send the traffic, let's say for example from here to these two group members. So I have like, for example, 3 options in total for the same. What I can do, I can go on this machine, and what traffic I want to send? I want to send a basic ping packet. So I can say ping 192.168.10.1. So one-to-one communication. And then again, I had to generate one more packet, 192.168.10.5 here at the end. So what happened actually here, that there was a multicast source. From the multicast source, I wanted to send the same traffic, some traffic to group member number 1 and group member number 5. So I need to generate, and I'm going to use unicasting for the same. So I need to generate 2 messages. One message that has the source IP as my own IP and the destination IP as group member 1 IP, and the second packet that has my own IP as the source IP and group member 5 IP as the destination IP. So same ping packet was actually being sent. Same ping packet here, same ping packet that we have. Same ping packet was sent to, first of all, 10.100 to 10.1, and the same ping packet was being sent from 10.100 to 10.5. Okay, that is unicast. Now, I wanted to send the traffic to these 2 devices. I could have used broadcasting for the same as well. And if you want to use broadcasting for the same, very simple. Just go onto this device, just go onto this multicast source, and just use the command ping 192.160. Either use ping 255, 255, 255, 255. It means like I'm going to, ping out of, I'm going to generate an IGMP packet, which will have my own IP as the source IP and the destination IP as 255, 255, 255, 255. And I will send it out of all of my interface. This is broadcast IP. This packet will be sent here, 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 out of all the interfaces. If you wanted to do the broadcasting only in a particular broadcast domain, if you wanted to do the broadcasting only in a particular broadcast domain, what you could have done, instead of using this, do this 192.168.10.255. That means the packet will now only be broadcasted in this broadcast domain only. That is the difference between this broadcast 192.168.10. This is directed only on a particular subnet, directed broadcast. Okay. So now what will happen? One ping packet will be generated by this machine. I'm going to say one ping packet will be generated by this machine. The packet will be sent here. Switch will receive it. It will flood it here. This will receive it. This will receive it, which was our task. But these devices will also receive it. And if they are able to successfully receive that ping packet, they will of course give you the reply as well, which will confirm that this packet was delivered onto these 2 devices and they have successfully received it. So if I do this ping, enter, five packets we send. No? In ping, we send 5 packets. So first packet, second packet, third packet, fourth, 5 packets in total. Now see carefully. See carefully. Here, I send the ping packet. The ping packet was delivered to all the devices, and everyone, 1, 2, 3, 5, everyone gave me the reply, which proves that our ping packet was actually delivered to all the destinations, not only on the intended group member. You can also confirm it from here. See, here, I send one ping packet. Here, one ping packet, one ping packet, one ping packet, and I got the reply from 1, 2, 3, 4 devices. I did not send 4 ping packets. Sender is sending one packet, which is being broadcasted to multiple destinations, and then all of those destinations are giving me the reply. If it was unicast, I need to send one packet for this, one packet for this, one packet for this, and one packet for this. So no. You open this ping packet, see, check the ICMP echo request packet. This is ICMP echo request packet. Open it, 192.168.10.100 to 55 to 55 to 55 to 55, broadcast IP. Then see, broadcast MAC address. It just cannot happen that your destination IP is a broadcast IP and destination MAC is a unicast MAC address. It will not happen. Problem of this approach is, problem of this broadcasting is that, okay, I need to send, the sender needs to send only one packet, but the problem is that that packet was broadcasted to everyone. Since everyone belong to the same broadcast domain, they have to receive it and they have to accept that packet. And since, how can I confirm that these have accepted that packet? I can confirm that these have accepted the packet because I am getting the reply from there. If these devices does not accept the packet, they will not give me the reply. But since they have given me the reply, it confirms that these devices have successfully received that packet. So unicast is not a very efficient way of delivering the traffic to multiple destinations. A broadcast is not also a very efficient way of delivering the packet to multiple yet specific destinations. Any questions, anyone? Let me know. Unmute, directly unmute you can.
Okay, in the packet capture, why the destination IP was showing 255, it can show the specific subnet, this one, right?
No. See, broadcasting will always happen based on the same. You will never see that 192.168.10.255. It is like, it is just an indication that I want to do the broadcast only in the broadcast domain. So ultimately, the destination IP will become 255.255. Destination MAC will become FFFF. That is just to tell this device that the broadcasting needs to be done only in a particular broadcast domain. That is for this device only. The packet that will be generated will have the destination IP and MAC as the regular broadcast IP and MAC address.
Okay. One more small query. If I want to check a group of server in the same subnet, I can ping with the broadcast IP address.
You can do that. If you want to, let's say, for example, actively see, like if, let's say, for example, in this broadcast domain, we have n number of devices and we want to find out like how many number of devices are currently active, and so we can just ping the broadcast IP of that particular subnet and you will get the reply from the intended machine, which will confirm that, okay, these are the devices available in that broadcast domain.
Okay, thanks.
So now our purpose, our aim is to actually send the traffic only here, only in this broadcast domain, and only in this broadcast domain. Only to this particular group member and to this particular group member. Okay. So what I'm going to do, I'm going to use a technique called multicasting for the same. I'm going to multicast the packet, which will be delivered to group member number 1 and group member number 5. So as simple as, first question is, how am I going to make a group? How this group of 2 group member going to be identified? How am I going to identify that the packet needs to be sent only onto these 2 devices? How this group of 2 or more maybe group members are going to be identified? And of course, like we might have a group of these 2 as well later on for some other multicast stream. So this is a different group, this is a different group. I want like to send some traffic on here and I want to send some traffic on here. So how that group address GA, how that group address is going to be identified? In IPv4, unicast addresses are class A, class B, and class C addresses. In IPv4, we have a dedicated range for multicast, that is class D address. So class D addresses are actually used. INA sets aside class D addresses for the use of multicasting. First 4 bits of class D addresses are 1110. That means class D address will always start from the 224. Remember, in class D address, there is no network part, there is no host part. This class D address, each and every class D address represents a group. That is why after these 4 bits, rest of the 28 bits in class D address, they are known as the group ID, which gives me 224.0.0.0 to 231.255.255.255 number of like multicast IPs, and each and every IP will represent a group of multicast receivers, group of multicast group members. So why we cannot assign the multicast IP on the network interfaces? Because in multicast IP, each IP represents a group. You can be a part of the group, but you can never assign the IP as an IP address onto your network interface card. In multicast class D address, every IP represents a group. It is not an IP address. 224.1.2.3. This is not an IP address. This is a group address. If a packet is sent to this particular IP, the packet will not be delivered to one. It will be delivered to every machine that is part of that particular group. It's like, for example, creating a group on your WhatsApp and giving it a name. So here the name is IP. You might have n number of people in your contact, but that group only includes a few of your contacts. X number of contacts in that group is there in your WhatsApp. So when you send the packet to group, it is delivered to everyone in that group, but not to the other contacts in your mobile phone. So class D addresses that start from 224 to 239, they are used for multicasting. And every IP in class D address represents a group. It does not represent an individual IP address. And that is why, since this IP in class D does not represent an individual IP address, that is why we cannot assign these IPs as an IP address onto the network interface card. In IPv6, we have FF range. FF00:8 is there in IPv6. Okay. So I am going to send a packet. No, there is no public-private concept in here in multicasting. Not at least so far. It's not a public-private. There is no public-private concept such as we have in IPv4 and IPv6 in multicasting. Like this is a normal range that we can use. That is correct that some of the IP range is used for private users. Some of the IP range is for the public users. So within this range itself, we have public and private, just like in Unicast addresses. Within this range itself, we have some public and private multicast addresses. This address 224 to 239 cannot be categorized entirely as public or private IP multicast address. Okay. So what I'm going to do, I'm going to actually send the packet from my sender, and multiple devices will receive the copy of that. If I am going to use IPv4 multicast, then the range, the multicast group address must be from this range 224 to 239. And if I'm using IPv6 multicast, that will be from FF00 range. Okay, no problem. So what I'm going to do here, now I am not going to ping from here. I'm not going to ping from here to each and every IP individually. And also I'm not going to do the broadcasting. What I'm going to do, I'm going to say ping and choose whatever. Consider, think, consider that what group address we have assigned to these two people, 239.1.2.3, maybe 4.5.6, whatever, it doesn't matter. 239.10.11.12, whatever, doesn't matter. 224 to this range, 239, 224 to 239, that way, not 231 actually. I think I somewhere wrote 231. 224 to 239 range is there for the multicasting. So let's say, let's assume here that these two group member, for these two group member, for the group of these two members, for the group of these two devices, I have chosen a multicast group address to be 239.10.11.12. So I am going to go on this multicast source and I'm going to say ping 239.10.11.12. Now, why are we using ping again? Because in your exam, they use the ping again. They use the ping as well to do the testing for the multicasting. So you have to use the ping. You don't need to run any application for the to generate the multicast traffic also. We can do that. We can use the VLC media player for the multicasting and everything, but we are going to keep it simple because this is what they have, what they typically ask in the exam. If they want to test something regarding the multicast, they will always do the ping. So you must know how this works. So from the multicast source, the source of the multicast stream is going to generate the packet. Which packet? Ping packet. And that packet is going to be multicasted this time to the multicast address 239.10.11.12. And I'm going to send like a lot of packets. Anyway, let's send one packet first of all. I will ping drop. Okay. Check the capture. Here, packet was generated. IGMP packet was generated. The ping packet was generated. This is the multicast packet. This is the multicast traffic that we are generating. Multicast traffic could be anything, audio, video applications, could be anything, video conferencing, audio conferencing, anything. Here, we are generating the ping packet. We are using the ping packet for the multicast traffic. If you open this packet, same IGMP packet is there, no differences at all. Same IP header is there, no differences at all. Same data link layer header is there, no differences at all. It means multicasting is not going to do any extra encapsulation or anything. It is just going to use the destination IP as a multicast IP and destination MAC as a multicast MAC. There is a relation between this and this. We'll talk about that. Now, this packet was received by the switch. Switch received that packet. It flooded. It basically sent that packet out of all the interfaces except for the interface where the frame was received. It was received here. It was received here. It was received here. It was received here. And I can show you that in the capture itself, if it has captured it. See, this is the capture of this link. So I can see that packet going from there. This right here is the capture of the last link. I can see that packet going on there. This is from switch number 1 to group member number 3. So I did the capture. I did the capture here. I did the capture here. And you can see here that the packet actually is being sent here. Here, of course, the packet will also be sent here and here. We did not capture it, but doesn't mean that it will not. It will be sent here and here as well. Now, when this device receives that packet, it decapsulates that packet. It checks the destination MAC address, and the destination MAC address is this one. This is a multicast MAC address. And since this device is not part of this multicast group, it will immediately drop that packet right here. The packet will not be processed here or here. We have decided that we are going to send the packet to this destination, and everyone will be able to receive and will be able to receive that multicast stream that is sent to this address. All the intended recipients will be able to receive this multicast stream. But the problem is that, have you told group member number 1 and group member number 5 that you are supposed to receive the multicast traffic coming from this stream? No. So just by using the multicast IP for sending the traffic is not going to work. Multicast IP, having a multicast IP to send the traffic to is one of the requirement. The second requirement is a mechanism by which these group member can join or leave that multicast group whenever they want. We must use some tool using which these group members will join or leave the group when they want. Tools such as your audio video conferencing tools such as simple as a media player, such as VLC media player. There must be some tool available by which these group members will be able to receive the multicast stream. Here in our GNS software, we don't have to use any special tool for the same. We just need to go on the group member number 1. We just need to go on the interface FA0/0, and I am going to make this group member part of that multicast group with the help of a protocol called IGMP. Group Management Protocol. Group Management Protocol. Internet Group Management Protocol is the protocol responsible to let the group members join or leave the group when they want. In fact, when you use those multicast applications, you use those applications by which you join or leave the multicast stream whenever you want, they actually use this IGMP protocol for the same purpose. So what I am going to do here, I am going to make this group member part of the multicast stream with the help of IGMP protocol. Command is IP IGMP join group 239.10.11.12. That is it. IGMP, Internet Group Management Protocol, has 3 versions. Version 2 is by default. So as soon as I hit enter, the group member number 1 on interface FA0/0 will enable IGMP version 2, and it becomes part of that group. As soon as it becomes part of that group, it will be able to receive that multicast stream successfully. And if it receives that multicast stream successfully, it will, in our case, it will give the reply. Because we are sending ICMP echo request. So if you receive the echo request, give the echo reply. Enter. As soon as you hit enter, right here, you should be able to get the reply. On the multicast source, I am now receiving the reply, which proves that my multicast traffic was actually delivered on group member number 1, not on group member number 5. Okay, I will go on group member number 5 as well. Same command. Command is interface FA0/0. Command is IP IGMP join group 239.10.11.12. It's like we have opened the application Zoom, and I had the link, joining link. I clicked on that link and I joined it. It's like opening your application from where you are supposed to join the meeting, video conferencing, audio conferencing. You enter the URL or invitation, click on the link that was sent in the invitation, and you just join that group. Enter. As soon as you hit enter, this group member 5 also becomes part of that multicast group, will successfully now be able to receive that multicast ICMP packet. And if it does, it will also give the reply. So 1515. I am still not receiving the packet from 2 and 3, which means these 2 are still not part of that group. It means my packet that I have sent is actually being delivered. Actually, it is being delivered to everyone, but only group member number 1 and 5 are able to receive and process it. And as a result, I can see the reply from there.
So on server side, did we configure anything where the
No,
interface?
no. On server, basically the stream is generated and sent. The stream that was generated and sent was sent to a multicast group address. And these were part of that group address. So they are able to receive and process that stream. That's it. We did not configure anything on. We don't need to configure anything here, to be honest.
Okay, means if I try to ping from non
Group members.
GM group member, also I will get that reply. Means
Definitely,
uh,
definitely. But that
on
has
the
to be unicasted.
no multicast packet only.
How can you will not get the reply now because they are not part of non-group member means they are not the group member, so they will not give the reply
No,
to
no,
you.
I'm not trying to ping from M source.
Huh?
Do I'm trying to ping from this non-group member PC to that multicast address.
No, but if you ping that, then you will become the source, no?
Yeah, means that have you configured anything that one the
No,
source?
no. If see, what does this mean? This means that you are generating the packet. This command itself means that you are generating the packet. This command itself is like configuring you as the multicast source. No extra commands are needed. So if you go on the non-group member and execute the same command, you will become the source of that multicast stream as well. You will also start generating that multicast stream and multicast it in this broadcast domain. And whoever are the member, they will give the reply and the reply will be received to you as well.
Okay, but the means on the recipient end only we need to configure the interface that IGMP. In the source
Yes,
side is
yes.
nothing.
No, on the source, we don't. Sender is not part of that group. No? Sender doesn't need to be part of the group to send the traffic. Sender does not need to be part of the group to send the traffic.
Okay, means if any application, any streaming application is running, means that needs to be run on M source, right?
Yes. You have to make
Uh,
sure that the sender is sending the traffic. The sender must send the traffic. To send the traffic, it will use some mechanism for the same as well. Like might be the sender, the multicast source is using some application to send the traffic. So that you have to make sure. But on the receiver end, you will have to join that multicast stream using some application. So that multicast streaming application must run on the receiver ends only.
okay.
Yes, the interface can be part of more than one group as well. Completely fine. So see what I do. Let me do one thing. So if I go on this multicast source is generating the packet for one group, and I go to the group member and I say IP IGMP group 13 as well. This group member is also part of this group. So this group member is receiving two streams, like from here and from here. And I will go to, let's say, for example, a non-group member, and I'm going to say ping 192.160, ping 239.10.11.13. So you will receive like the reply on here as well. So this device is part of two multicast group now. One multicast group, this one, and one multicast group, this one. So if it is receiving the multicast stream from here as well as from here. That is why you are able to see the reply here and here. In the reality, it's not like this group member has to give the reply to the multicast source. It is, we are using ping ICMP. That is why we are getting the reply. And it is a confirmation that this group member has become part of two actually multicast streams. So completely possible. I can leave the group by using the no keyword. If I want to leave the group, I can just use the no keyword for the same. So that I leave the group and the package will get. And you see here, the device doesn't need to send multiple ping packet. You can see here that the device is sending just one echo request and getting reply from the intended machines. One echo request, one packet, multiple reply, one packet, multiple reply. Why multiple reply? Because multiple group members. So there has to be a mechanism by which the group address is identified, by which the group members actually become a group member, by which some devices become a part of a group. That mechanism by which we identify the group address is the class D, or that FF00 range that we have in IPv6. That group address is what we refer to as the multicast IP address. So there has to be some multicast IP addresses by which the group is going to be identified. That is one thing. Second, there has to be a mechanism by which members can join or leave the group. And that is done with the help of the protocol IGMP. Comes in total 3 versions. Version 2 is the iOS default. You can check it here. Right here you can see. You must be a member of the group to receive it. You must be a member of the group to receive the data, but you don't have to be a member of the group to send the traffic. So the sender doesn't need to be part of the group to send the traffic. Sender can send the traffic to the intended receivers anytime they want. If you send a packet to the group address, all the members of that group will receive it. Class D in IPv4 and in FF00:8 is the result for the IPv6 multicast. So this is a non-group member. It can send the multicast stream and can be received by these devices. This is a sender and receiver both. A device can become both sender and receiver. Think about the video conferencing, audio conferencing, where the sender can become the receiver as well. Both the people can communicate at the same time. So sender can be a receiver as well. It's not like there will be a dedicated sender, dedicated receiver. In a communication, in a video conferencing, audio conferencing, like multiple devices can transmit and receive at the same time. And these are some commonly known multicast addresses of class D range. So if you send any packet to 224.0.1, it will be delivered to all the systems on the subnet. If you send a packet to 224.0.1, it will be received by all the routers on the subnet. If a device multicasts a packet to this 224.0.1, it will be received by every device. And if you send it to 224.0.2, it will be received only for the routers on the subnet. .5.6 used by OSPF, .9 used by RIP, .10 used by IGRP, already know about that. And 224.0.13 is used by something called PIM, Protocol Independent Multicast routers. Apart from these common ranges, we also have some ranges starting from 224.0.1. Other reserved ranges are 224.0.1, which are not local in scope, means that the packet can be transmitted with the detail value greater than 1. Any packet that is sent to this destination can have the detail value more than 1 as well. That means they can cross the broadcast domain, such as NTP, Embrace, Tibco Multicast, whatever it is. So these are some 224.0.1.0/24 range is also a reserved range in multicasting that can be used to transmit the traffic from one broadcast domain to other broadcast domain in a multicast fashion. So 224.0.1.0/24 range, which are not local in scope, means the packet for these destinations can be transmitted with the detail value greater than 1. And this is the private range. This is the private range in the multicast. If you want to use multicasting within your organization only, you can use these addresses for the same. There are 2 raised to the power approximately 24 addresses, which are way more than enough for your enterprise network to support. Administratively scoped addresses, 239 range is for private users. Private address, similar to IPv4 private address, unicast addresses that we have. These are not for the global internet traffic. Same addresses may be used in different locations for multicast sessions. So for example, in a specific site, if you want to do the multicasting, we can use this range. And for the entire organization, if I want to do the multicasting, then I can use this range. Private IPs. No? These are the private IPs for multicasting. 239 range is the private range for the multicasting. You can use it in a you can use it to perform multicast routing in a site, and you can use it to perform the multicast routing in the entire entire organization as well. And then there is a special range, 232 range, which is reserved for something called SSM, source specific multicast, targeted for internet style broadcast. We'll discuss that later on. What is source specific multicast? So these are some reserved ranges like this, this, and this. This you can use. This typically we use in our production environment for the private traffic. We are not going to multicast like worldwide. Like we are like the companies that are supposed to send the traffic to like over the internet, the multicast traffic. They can use the other ranges, the public ranges, but for the private users, this range is sufficient. Okay. Multicast MAC is automatically derived from multicast IP. So whatever multicast IP is there, multicast MAC is automatically derived with the help of the same. So for example, what multicast IP I use? 239.10.11.12. With the help of this multicast IP, the device automatically derives the multicast MAC address. How it does that? MAC address is 48 bits in total. First 25 bits will remain exactly the same. First 25 bits will remain exactly the same. 01005E0. First 25 bits will remain exactly the same. In a multicast MAC address, which is derived from the multicast IP address, first 25 bits will remain exactly the same. And the last 23 bits are derived from the multicast IP. Last 23 bits of this multicast address is derived from multicast IP. So convert this multicast IP in binary and take last 23 bits and write them down here. So I converted this into binary 8, 8. So 8 bits, and from here 7 bits I have to take. 8 plus 8 plus 7 is equal to 23. First 25 bits in the multicast MAC address will always remain exactly the same, 0100FE, 5E and 0, and the last 23 bits are going to be derived from the IP itself. So of course, like basically just put last 2 octets as it is here. So 12, 11. And here 10, convert this in binary. So 00001010, this is 10. And take the 7 bits from here and write those 7 bits here. In the second octet here, set 7 bit from the second octet. Last 7 bits from the second octet we have to write down here. So 0, and it will be like 00001010, which is going to come like 10 as well. And then write that down in hexadecimal. So what is 10 in hexadecimal A, what is 11 in hexadecimal B, and what is 12 in hexadecimal C. So multicast MAC address will become, with the help of this, the multicast MAC address becomes 0100FE0 and ABC. Convert it into the hexadecimal. Convert this into the hexadecimal. So this is like 00001011, 00001100. Convert it into the hexadecimal. So you should know how to convert binary into hexadecimal. So 4-bit here, like 4 group we have to create and then write them down in the hexadecimal. So 0A, 0B, and 0C. You must know how to convert from the binary to hexadecimal. So write that down, write the 23 bits of the write the last 23 bits of your IP in binary and convert it into the hexadecimal, from binary to hexadecimal. To convert from binary to hexadecimal, we make a group of 4 bits, and write them down, 4 bits, 4 bits. Here also 4 bits, 4 bits. Any multicast IP that is given to you, 239.10.11.12, with the help of this multicast IP, I can get the multicast MAC address. To get the multicast MAC address, starting 25 bits will remain exactly the same, and last 23 bits are going to be derived from the IP itself. So convert this into the binary. Convert this into the binary and write that down. Write last 23 bits of it here. And then convert it into the hexadecimal. So if you, for example, write down 12 in binary, it will be 00001100. If you write down, let's say, for example, 11 in binary, it will be 00001011. If you write down, for example, 10 into the binary, remember you have to take only and only 7 bits from here. So 1010 and 000. And the 8th bit will always be 0 here. So now 4, 0, 4, A, 4, 0, 4 here is B, 4, 0, and 4 here is C. This is how we convert from binary to hexadecimal. And then write down the multicast MAC address respectively. Multicast MAC is automatically derived with the help of the multicast IP.